Let's see now the components of the action potential. Before we start, I need you to remember that the neuron, when it is at rest, it has this resting potential, which is the minus 70. And during the resting potential, the sodium is kept outside and the potassium is kept inside. Okay? Even if there is some leakage of, say, for example, potassium getting outside or sodium getting inside, the sodium potassium pump can match the rate of this leakage. So let's say the pump works 1 round per minute, which is of course not true, but let's just for simplicity. And the leakage rate is 2 potassium, 3 sodium, 2 potassiums out, 3 sodiums in. So the pump per minute or per cycle, it can take these 3 sodiums out and bring the 2 potassium in to maintain this resting potential. Now, when there is a stimulus, this stimulus would cause a change in the resting membrane potential. This stimulus, what it will do, it will open the sodium gates. So now sodiums or sodium ions overwhelmingly rush inside the neuron. They are rushing inside the neuron. This will change the membrane potential toward more positive value, and that is depolarization. So here the membrane potential would move from minus 70 to plus 30. It loses its value. That is depolarization. So during depolarization, we have sodium channels open, sodium diffuses in, and the membrane depolarize. But remember, for the neuron, neurons do not like sodiums, a lot of sodium inside. So the neurons now are not happy. And they want to stop this and also to restore the minus 70. What they will do, they will close the sodium gates. They will open the potassium gates now. Remember, they have a lot of potassiums inside. So they will open them and let them leave the neuron. That would cause the membrane potential to come back, to restore the membrane potential. And that is repolarization. It's kind of readjusting. Repolarization. Here we have the sodium channels closed, potassium channels open, potassium diffuses out, and then the membrane repolarized. It means it returns to its resting potential, which is the minus 70 millivolt. Now, because of the nature of the potassium channels, when it stops slowly. So we will have like a short period of time. Let's use blue. We'll have a short period of time. That is the reestablishment of the resting potential. Reestablishment of resting potential when the potassium channels close. But basically, the components of the action potential are the depolarization and the repolarization, and then the I'm not sure why I'm not able to say it, but anyway, reestablishment of the resting potential. So these are the 3 components of the action potential. Now, since action potential is extremely important in the nervous system, and all of this communication is happening through it, so it has some rules that it follows. 2 major rules are that the first one is called something called all or none. It means that either we have full action potential or none. Okay, so if the changes reach the threshold, then it triggers. But if the changes are not, then there is no need to initiate an action potential. Actually, let's go back to here. See here, for example, these are some changes in the membrane potential, but they are not reaching the threshold. Then there is no action potential. But if the changes arrived at the threshold, then we will get an action potential. All or none also means there is no like 50% action potential or 80% action potential or 30% action potential. Okay, so either we will get 100% action potential or 0% action potential. So there is like no midway action potential, or there is no weak and strong action potential. Either we have action potential or we don't have action potential. So this is the first characteristic of action potential. The second one, it's something called self-propagating. It means that the action potential keeps regenerating or propagate itself in the next region of the axon. So it moves like a wave down the axon with constant speed and amplitude or power or intensity. So it moves as a wave with the same intensity and same speed across the axon. So you won't see like, hammering down on the intensity of the action potential, or you won't see like long, then short, then long, then short action potential. No. It always maintains its intensity, its speed, its time. Everything is identical. Everything is identical within the action potential. Now, in addition to that, we can have more action potentials for stronger stimulus or stimuli. So if we have more stimuli or stimuli, it means we have more action potential. Now, all of these action potentials still, they are identical, but their frequency or the period of, between them are minimized. But still, they are identical. They are either happening or not happening or not happening. So they are still following the all or none rules. So stronger stimuli generate more action potential per units over time. Also, and we talked about this, while the speed of the action potential in the neuron is constant, different neurons can have different speeds for action potentials. Now, again, to make sure, we said within one neuron, this is one neuron, okay? The speed of action potential is constant within one neuron. But if we are combining two neurons together, we might have different speed of action potentials. Usually, greater or wider diameters or larger diameters of neurons will have faster action potentials, whereas smaller will have slower action potentials.